A ransomware payload executes inside a multi-node hospital network. Within minutes, critical operational files are encrypted and the facility's digital infrastructure is locked down. The immediate reaction of the hospital's IT operations team is to wipe the affected drives and restore from backups to get the system back online. But a digital forensic investigator has a completely different objective. The investigator must systematically answer exactly how the breach occurred and who is responsible, and they must do this without destroying the digital crime scene. This discipline is digital forensics, the strict identification, collection, preservation, analysis, and presentation of digital evidence. If the hospital treats the ransomware attack merely as an IT outage to be fixed, they will overwrite the specific digital artifacts required to make the evidence legally admissible in court. The modern digital crime scene extends far beyond a single desktop computer. Today, evidence resides across smartphones, IoT medical devices, cloud servers, and raw network traffic. Organizations deploy this exact investigative methodology across corporate security domains to track insider threats, intellectual property theft, and employee misconduct. Looking at this photograph of the Europol headquarters, we see the international scale of the law enforcement cyber units that rely on these protocols to dismantle global hacking syndicates. At its core, digital forensics is the rigorous architectural translation of volatile electronic data into mathematically verified truth accepted by a court of law. Back in the hospital, the investigator's first step is to physically isolate the specific workstation identified as patient 0. Unlike physical evidence, digital data has two unique characteristics. It is highly fragile, meaning it can be easily altered or destroyed, and it can be perfectly duplicated. This schematic compares a computer's volatile RAM with its persistent hard drive. Volatile memory requires continuous electricity. If you cut the power, any active data held in the RAM disappears immediately. This creates an operational danger. If the IT staff simply pull the plug on the infected computer to stop the attack, the active malware processes and network connections currently stored in that RAM will vanish. To prevent this data loss, the investigator's first technical maneuver is to capture the exact state of the volatile memory before the system is powered down. The central paradox of this discipline is that an investigator must capture a system's precise operational state without the act of observation altering that state. Once the machine is secured, the investigator follows an absolute rule: never conduct analysis on the original storage device. This animation compares two copying methods. A standard OS copy alters file metadata, updating markers like the last access timestamp. A forensic image bypasses the operating system to map the exact sectors one-to-one, including the empty space. This bit-by-bit imaging uses specialized tools to create a flawless clone of the storage device. To verify the clone is exact, investigators use cryptographic hash values. Algorithms like MD5 or SHA-256 process the data to generate a unique alphanumeric string, acting as a digital fingerprint. This fingerprint perfectly matches both the original drive and the forensic image. Digital evidence is mathematically fragile. If you change a single bit in the forensic image, the resulting hash value changes completely. Alongside this technical verification, the investigator establishes a chain of custody document. This administrative paper trail tracks exactly who handled the evidence from the moment of collection straight through to court presentation. The strict combination of an identical cryptographic hash and a pristine chain of custody provides the incontrovertible proof required to validate the evidence's integrity. With the forensic image cryptographically secured, the investigator can now safely parse through the duplicated data for clues. They are searching for artifacts, the residual traces left by user activity or automated system processes. These include browser histories, user login records, and hidden system locks. In a complex ransomware attack, analyzing just the local hard drive, computer forensics, rarely provides the full picture. The investigation has to span multiple technical domains. Through network forensics, the team analyzes packet captures and traffic logs to map the malware's exact entry vector into the hospital. Simultaneously, malware forensics involves reverse engineering the malicious software found in the artifacts to decode its encryption behavior. Modern forensic analysis requires cross-referencing these artifacts across memory, disk, and network domains to meticulously reconstruct the attack timeline. While this methodology is rigorous, investigators are fighting an asymmetrical war against severe technological bottlenecks. This animation illustrates the challenge of scale. Modern investigations require sifting through terabytes of data, making analysis incredibly time and resource-intensive. Furthermore, criminals actively deploy native encryption to hide their tracks. They use tools like virtual private networks, encrypted messaging apps, and locked drives to scramble evidence into ciphertext. When that encrypted data is hosted on distributed cloud storage, the evidence scatters across multiple countries, creating a maze of international legal jurisdictions that delays collection. Attackers also deploy active anti-forensic techniques to purposefully destroy evidence, using methods like file wiping, log deletion, rootkits, and steganography. Steganography is the practice of concealing a secret file, message, or image within another seemingly ordinary file. Cybercriminals systematically exploit data volume, encryption, and decentralized cloud architectures to outpace the speed of legal forensic analysis. These bottlenecks are the direct result of computer architecture scaling exponentially over the last 40 years. Looking at this photograph of a 1980s mainframe, we see the physical isolation of early computer forensics. Cases involved localized crimes, like financial fraud contained entirely on a single machine. The 1990s internet boom and 2000s expansion introduced distributed cybercrimes like botnets and phishing. As seen in this image of discarded mobile phones, the explosion of personal devices forced the field to rapidly adapt to a mobile environment. Today, as this photo of endless modern server racks demonstrates, investigators must untangle dynamic, virtualized systems running blockchain, AI-generated data, and complex global networks. The physical scale of the technology has shifted from isolated mainframes to global IoT networks, but the foundational requirement for rigorous evidence preservation remains exactly the same. Back in the hospital case study, the forensic team successfully matches the network traffic artifacts to the malicious processes they captured from the volatile RAM, identifying the exact source of the ransomware infection. Because bit-by-bit imaging and strict chain-of-custody protocols were followed at every step, these technical findings can now be submitted as a formal legal dossier. This visualization represents the ultimate objective of the discipline, uncovering scattered objective facts and locking them together to present scientific findings in a legal context. Digital forensics is the vital scientific framework that transforms vulnerable, invisible code into incontrovertible truth in the courtroom.